Um, Hi, I'm Julian. Let me share my screen, see if that works. Okay, can you see that? Can you hear me okay? All right, so yeah, so Jen's stuff was really impressive to me, especially because there's a bunch of overlap. I was really into the PDB stuff. You'll see some slides about that, and into proteins. My background is in physics, and whoa, how do I do this? One sec, yeah. Okay, here we go. That's really the first slide. And I'm gonna, oh, before physics, I was a painter. That was I did this when I was 19. That's a self-portrait. I just give you a quick like run over my whole life. Let me see what time it is so I can don't go too long. All right, cool. So I started out painting and drawing, printmaking, and that was like my passion. But then I wanted to go to Berlin to the art academy, but then I ended up in philosophy of science, came across physics, quantum physics in particular, and I was like thinking, if I don't learn this, I can't believe what's being told in what we are learning in quantum physics. It's so counterintuitive, it's so crazy that I can't really afford to just believe the science writers. I have to actually study it myself. So I ended up going to the Freie University in Berlin. And then after like 8 years or so of the places, including Edinburgh, I ended up for my graduate research in Vienna. I'm not going to go into much detail here of this experiment. What my graduate research with Zeilinger in Vienna was about was essentially the replication of the old double slit experiment. Here's the 1802, the picture. You're probably all familiar with that. You take light and show that it actually behaves like a wave. But then, of course, Einstein came along, showed that light also behaves like particles when you measure it. And then the crazy thing is that when you take particles like atoms, electrons, or even molecules, they too are not only particles, but behave as waves. So what we did is take that exact experiment in principle. We did a double slit type of setup and sent at that point in 1999 the largest molecules. These guys here, those are buckyballs, Buckminster fullerenes, consisting of 60 carbon atoms. The most massive particles through this double slit type of experiment. Here's a schematic that I drew at that time for the paper, and we show that they too behave as waves. That means that's a setup in real as a photo. That means what we measure at the end is an interference pattern. So what is measured as a single particle, as a single buckyball, 3 meters away from the source where it goes out, has been going through 2 openings at the same time. So we measured as one particle, but the quantum wave was spread out 100 times the diameter of the buckyball. We call the buckyball, it's like about 1 nanometer diameter, but these slits are 100 nanometers apart. So imagine you shoot a soccer ball through two doors that are 100 meters apart, and they get detected at the moon. That's the same experiment scaled up to that proportion. Soccer ball, of course, is the geometry of the buckyball. So it boils down to this visual metaphor, though. So that kind of captures the conundrum here, you know. So everything is okay until you realize something's really, really off here. So that's a slide I just added recently to a talk when I gave a talk about quantum physics and psychedelics, which is also another interest of mine. So all the stuff that's really interesting about our worldview, about the world that we feel, that we see, is basically not allowed in a materialist, reductionist, Newtonian world. But if we enter the world of quantum physics, suddenly all that opens up to become a possibility. That's one of the reasons this stuff is so interesting to me. So I started. So what happened? So I did my graduate research in Vienna. Then I met this woman who studied neuroscience, who did her PhD in neuroscience. And I asked her, what shall I use as a next molecule? Because we wanted to go from the buckyball to the next step. What would be eventually the goal would be to send the philosopher through the double slit, so you can experience what it means to be a quantum object. And so then the woman I met, who became my girlfriend and later my wife, so told me about these green fluorescent proteins she uses to tag in brains, like a specific molecule. So it's like a protein from a jellyfish. I was super intrigued. I looked it up on Google, which was brand new at that year, and I was completely blown away by the structure. And a few years later, I then moved to her. I moved to Portland actually the next year. And after I did my thesis, I finished my thesis. And then I enrolled into art college because I was thinking, what the hell am I doing here? I didn't want to do science anymore, so I want to go back to art. And so in one of my first classes in art college, I made a miter cuts wood sculpture. In German, it's Gärungsschnitt. I don't know. It's that kind of process. You can take a one-dimensional building material and do these compound mitered cuts, and then you flip each other part, put it back together, and you get from a one-dimensional thing to a three-dimensional thing. And that intrigued me because I had, from my studies of proteins, which were involved in my expanding my research, I realized that proteins do exactly that. You have a one-dimensional strand of information, and by virtue of chaining these amino acids together and then in very specific configurations fold them into space, you go from a one-dimensional to a three-dimensional object, which is our bodies, so that in between is the protein. So that's why I got really interested in proteins at that point. And so I started, I wrote my own software that allowed me to go from the PDB data points, in particular the carbon alpha carbon atoms of the backbone, to cutting instructions. So I have dots in space, and then I get out of my software cutting instructions to make, as an approach to make 3D sculptures based on the backbones of proteins. So that's how I got into this kind of thing. And then I tried to make my green fluorescent protein. It totally failed. But the good, cool thing about art is you can, instead of saying it's a failure and trashing it and telling nobody about it, you can just put it in a gallery and call the piece failed protein biosynthesis. So that's a piece of art right there. There it is. So here, then a few years later, I realized I have to pick up welding because otherwise I couldn't pull it off structurally. And that's actually a green steel jellyfish. It's the green fluorescent protein structure, which is at the Friday Harbor labs where this molecule was first isolated from the jellyfish and identified. That was actually before the Nobel Prize. The Nobel Prize came a few years later for this thing. Then another piece talking about visual metaphors, Philip. So that's another thing I'm really interested in too. Of course, there's the human antibody, and this is a composite PDB structure we're showing here, which is partly analyzed from crystallizations, the three different blobs there, but then it's the hinge region is modeled basically by minimizing energy altogether. And I was asked by the new Scripps Institute in Florida to propose a sculpture based on this antibody. And I got really intrigued with this. And I realized this beautiful analogy between the human body, here visualized in the 15th century by Leonardo, of course, and the human antibody. And it's not only, actually, this is just a proportional scaling. It's not distorted in any ways. So that actually fits really well. But also, the hypervariable regions at the ends of these wings there, that's where we humans have fingers, and that's where the molecule changes the little bit of structure just to attach to very different pieces of bad guys that intrude your body and tax them that way, so the immune system can get rid of them. So that's why this thing is called Angel of the West, because they're like an army of angels. That was my sense. Yes. So then the learning curve, of course, coming from a science background, is that you have to pull things off in real space and against gravity and corrosion. So that's a really tricky one. It took me years and years to figure this out. Here we built a 3 meter by 3 meter, approximately, no more, 350 or so stage. It's 12 feet by 12 feet to build this, to get the third dimension in. So you can see there's a 2D printout on the bottom, and then the third dimension is like these pieces of 4 by 4 there. That's the piece completed, and here's the piece on site. That's the Scripps Institute that they opened back then at as a branch of the one in Florida, in California. And then you were talking, Janet, about the PDB. They, of course, were my good friends all the time because I used all their data to make my proteins. And I ended up being asked by them, they opened in 2013 or so, they opened at Rutgers University their own Center for Proteomics, Integrated Proteomics, it's called, where they house now the PDB, well, since then. And they asked me to do a piece based on collagen. So I came up with this piece here. That's there in New Jersey. And it's about 20 feet tall, which is about 6 meters. And speaking again about metaphor, my interest was to put the 3 primary colors into each of the strands. We call it synergy because it's so much about, stuff doesn't work by itself, but in the concert together, it makes something new. Just like the primary colors create essentially all the colors out of this basis system in a mathematical sense of 3 colors. Here, let's go back to the buckyball for a second. That's my old boss, Zeilinger in Vienna, holding his birthday present for his 70th birthday. I made him the buckyball in bronze, which was actually the first piece I made in my garage when I graduated from art college, which is cool to me because it actually echoes in its structure. The nested structure echoes the quantum mechanical wave function of the buckyball. If you emanate from a point source, you get these concentric shells essentially. So it's neat in different ways. Then I kind of got carried away with buckyballs for a while. I made this large piece, 30 feet diameter, which is about 10 meters, 9 meters. There it is. Because I'm really intrigued, again, metaphor is, how the constructivist space of math and science intersects with the natural space that the trees represent here. Then I looked at the buckyball and I realized, why do I love it so much? It's actually a special case of a regular foam structure in 2D. And so I asked myself, how can I make this into something in 3D? And I came up and I realized that foam structure does fit the bill. And so I played with that. That's a very, very tiny sculpture out of polystyrene. And then I went another spin-off here is my safety screens for my windows, because I'm in the kind of shady area of town. So I didn't want prison bars. So I invented my bubble windows, which is cool because you actually seat them in there and then you let the physics do its energy minimization, surface tension minimization. And you see how each of the junctions on the center become Mercedes stars, 120-degree stars, whereas the ones that sit on the boundary are sitting 90 degrees. So that's a natural outcome of the energy minimization, which is not only really beautiful, but also actually structural. Then another spin-off of this foam research was looking into algorithms that optimize how do you describe a 3D solid in the computer. So the one typical way of doing it is with these triangles. They get distorted along the direction of low curvature. They're narrow. The direction of strong curvature, no, sorry, the other way around. So where you don't need much curvature to describe it, you can keep them long. And the other direction, they get narrow. So it's in essence, this is again what the foam does in nature. It's a sort of an energy minimization. In this case, information minimization, which also leads to the same kind of beautiful results. So I used those algorithms to design a bunch of pieces, including this one, a larger one that really kind of pushed our limits in the shop in 2015 when we built it. It took us 8 months to build it. That's made out of stainless steel. She's holding this, it's a Texas Tech University. She's holding a agave plant, which is a really important plant in that area for the traditional peoples have used it for a number of uses, pretty much everything you can imagine. Here's like some photos of us tacking this thing together, lots of numbers, again, custom software, protractors being used and the computer in the shop. So it's kind of, we're pioneering as we go to kind of like develop these new approaches to pull stuff off in actual 3D. That's the face of her. And that's the inside. Chuck sitting inside and welding the insides. There she is again. So that was just, oh yeah, another triangle piece. That one is slumped glass. I laser cut each triangle, slumped glass in it, then put the piece together and then glued the glass on the inside. So the gravity had slumped it, so it's bulging out. Oh, there's actually a little video, so you see it a little better. Oh God, my timing is actually awful. Wow, let me just really go through this really quick. Okay, you're speaking 2D to 3D, so that's what's one of the results when you go from triangles to the bulk tetrahedral, irregular tetrahedra. Engineering has algorithms that provide us with this. I'm not going to show the video; it takes too long.
Julian,
yeah.
Sorry to interrupt, because we have one speaker less. We're actually not in a rush. I love it.
Oh, really?
From my
okay,
side,
cool. Okay.
no need to
right,
rush. You can finish in peace. I'd love to see it.
All right.
Sorry
cool.
for interrupting.
Okay, so this was just irregular tetrahedra here. And then this is basically, if you think about like icosahedron and dodecahedron, that's called the dual in mathematics. And if you go through the motions to go from an icosahedron to a dodecahedron, I realized if I do this on my computationally for complex solids to do the solid, to do the dual, I realized that if I skip one step at the end, I get these really beautiful foamy patterns. So this is I just ran with that. This is an interesting piece to me. That's at Georgia Tech in Atlanta. I actually, it's made out of bronze. I did little 3D printers. I bought 8 of these little 3D printers, made all the pieces in plastic, glued them together in chunks that the foundry can handle, and then cast those in bronze, and then weld together in the shop. So that was interesting from that point of view alone for me to figure out that we can actually do on the cheap 3D printing that ends up being metal. Well, on the cheap, it's not really cheap, but it means that you can do it comparable to an actual traditional bronze handcraft, not real 3D printing like the rocket people do. That's really expensive still. Okay, so then this experiment with the buckyballs like kept with me, and I, as I said, I was really interested in that idea of I am the quantum object. What would it feel like? And if you actually look at the math, if you move this way, you know, the quantum waves that quantum mechanics dictates, like are basically arranged perpendicular to the direction of motion with sort of equal spacing. So the most natural way of visualizing this was to think of a human body in the motion of walking, consisting of wave fronts in perpendicular to the direction of motion. And so in 2006, I made this piece without really thinking about how it would look like. I just made this 2.50 meter tall styrofoam block, and then I carved it out. I just did this ridiculously simple stylized drawing and then carved it out. And then I made him out of these slices. In the next, first I traced them and cut them out with a plasma cutter. In the next iteration, I used a laser cutter and was able to then turn it into addition, which in turn allowed me for the first time to make money, which was amazing, and I didn't expect that to happen. But the really interesting thing that happens is obviously the most obvious thing now is that it disappears when you look from the side. All these sides are parallel, you see 90% air, and what's behind it on that specific disappearing angle. And that's one of the main things I ran with over the next years after that. There's a bronze version on the right. And as you can see, it does really cool things with light. And then that culminated in 2014 in a large commission for the University of Minnesota. That's the Nanotech and Physics and Nanotech building, I think it's called. And I was intrigued by the idea that I could use this technique to make very figurative pieces, very traditional on one hand, but very different on the other hand. And I could use that I tap into the history of art basically by kind of talking about the difference, you know, between science and the rest of the world. I have this man in a very uneasy pose, sort of guarding this building, and the woman in a very easy pose, kind of watching in from the outside. So that was just really interesting to me. Spannungsfeld means tension field. It's hard to translate. It's being used metaphorically. It comes from electrodynamics, the word, but it's used metaphorically today. It means the tension between two opposites, polar opposites. Here's a quick video so you get a sense for how it disappears on you. And that's 2014. That's now 11 years ago, and that's when I established this kind of techniques, which I could pull off by advances also in 3D scanning technology. So I was then able to use the rudimentary early, you know, ways of scanning machine parts mostly, but I used that to scan people, to do 3D scans of bodies. And that's what I'm still doing today. And I'm using that a lot, and it gets fairly sophisticated. I have my own 3D setup here. That's then a few years later, I started experimenting with light. This one is illuminated from the inside, from below. And you can see it gets very attractive to it. So it's like, it allowed me to kind of like navigate this thing from scientists go like, oh yeah, that's cool, to people go like, wow, that's cool, without having any interest, idea, or whatever concern about this, the science that, you know, guided me towards this. Those are some larger pieces. That's actually a commission of the collector's 4 kids. I made the actual portraits of them. There they are where they're installed. That's in Mexico. Disappearing angle. And then another natural thing as a quantum physicist is to think about how stuff intersects, how stuff goes together. And of course, humans, we do this, you know, we're individual to perceive ourselves as this person. But at the end of the day, after our life and probably before, but somehow beyond, it feels very much like we're coming from a common oneness. And that's something we can talk easily. Also in quantum physics terms, it's like when atoms get cooled down, the wave functions start overlapping with each other and they condense into Bose-Einstein condensate. That's one of those guiding metaphors in my mind, you know, that made me, for example, design this piece. That's a group of people, and there's spots where they pop up individually as faces, but somewhere down there, you can't say that's this person or that person, you know. And the same is true for that chicken, you know, the chicken and the humans. It's really, at the end of the day, there is only oneness, even if we make all these artificial boundaries between us and other species, you know, genders, skin colors, whatever, wherever you want to draw that line today. That's a relatively recent project from last year where I was asked to make an astronaut and I refused to do it. And then the guy talked me into it and I got really excited about it at some point because he was this Russian kid who was interested in cosmonauts and then moved to the US and then had this kind of really intriguing kind of history about in his own worldview and mind about what the astronaut means. So I made this piece out of mirror polished stainless steel, but because mirror polishing and welding is really hard to combine, I made it out of with these 6,000 little screws. And completely unexpected for me, I just took this quick video for Instagram and it ended up racking up over 90 million views. So that was completely shocking to me. And there's not even music on there. So that's me being, you know, reflected on the sides there. And it's really neat. It's a cool piece. Like I use this now a lot too. The mirror polished also with so-called particle vapor deposition, but you can color mirror polished stainless steel. So I'm working with a lot of new kind of materials now, which is very fun. So thank you. That was my timing. Yeah.